Hey everybody, how's it going? Today I'm going to talk about how you can assign point groups quickly for certain geometries if the ligands are the same. And then I'm going to talk about going through flowcharts to find point groups. But first, I know I mentioned last time, and maybe probably the time before that, if it's tetrahedral and it has all the same ligands, it's TD. Octahedral, it's OH. Trigonal bipyramidal, we could do an example, but it's D3H. Trigonal planar is also D3H, and squared pyramidal is D4H. If I left anything out, just let me know. I think I already went over linear molecules, so those are either D infinity H or C infinity V. And you can also generalize that all planar molecules are pretty much in the D family because they're going to have at least two symmetry axes that are, well, they're going to have perpendicular symmetry axes. So benzene, for example, is in the D6H point group. It's planar, and you've got the primary rotation axis of the C6, but then perpendicular to that, you've got a C2, because obviously you can just flip the benzene ring around. So as far as the flowcharts go, first you're always going to want to ask, is it low symmetry? And remember, the low symmetry, there's three groups. You either have C1 or just C, and all you have is the identity operation for that. And then the second possibility, you've got CI, and all you've got is an inversion center. And then finally there's CS, and all you have is a reflection plane. Sometimes those are a little hard to remember. You can get them mixed up. CS in particular, because you're like, why is that S there? But it's only got a reflection plane. You don't have to use it that much, so that's always the first thing you ask yourself. And then you ask, is it high symmetry? Again, like one of these right here. And if not, then you start talking about rotation axes. And rotation axes are really how you group the rest of them. And then after you find the rotation axes, you start grouping it by reflection planes. So first you want to know, does it at least have two perpendicular C2 axes? So what I'm talking about is a planar molecule, for example. If it's trigonal planar, for example, it's going to have a C3 right down the middle. And I'll show you what I'm talking about. That has a C3 looking straight down, and then if you rotate it, it's got a C2 going perpendicular to that. Because obviously you can just switch that like that, and you can switch that one like that. And then, like I said, going straight up. Okay. So if it does, and that would be in the D family. This is a D family molecule right here. If it does have two perpendicular C2 axes at least, then it's in the D family. And then from there, the D family is easy. It's either going to be DNH or DND, where N is the primary rotation axis. So this is going to be D3H. And the way you figure out if it's H or D is, if it's H, there's going to be a mirror plane that is horizontal to the primary rotation axis, or it'll be perpendicular to it. So you can see here's a primary rotation axis, and this actually has a mirror plane. Again, we'll draw it like this. And the last hydrogen is going straight back into the board. You have a mirror plane that goes straight through here like that. But your C3 axis is right up and down. So that puts it in the H group. However, if it did not have that, if it was something different, perhaps you had an H down here, and it was trigonal pyramidal. Not bipyramidal, just pyramidal. That would be D, because you you would not have this anymore if you had that H there. So basically, you just have to find the primary rotation axis, which is going to be the highest number of rotations, or the highest in number for the rotations. And if it has a plane, mirror plane horizontal to that, it's H. If it does not, it's D. Now the C family is a little bit more complicated because there are a couple more subgroups in it. But let's look at a C molecule. I know we usually use water, but I'm just going to use it again because it's quick and easy. Water is a C family molecule because you only have one primary rotation axis. See, these H's are going to switch 180 degrees. So you got that C2 right down the middle. And because water is actually not linear, you can't put a reflection plane through here like this. You can, however, put one through all of the atoms. Alright, we'll do it like this. If you look straight down on water, and there are the lone pairs, and these are actually facing up towards us. It has a reflection plane right through there. And the C family is a little different. If it does have a reflection plane that's horizontal to the primary rotation axis, it's in the C in H family. If it doesn't, it's in the C in V. Now remember, up here in the D family, it was D in D. So now it's going to be C in V. So water, I think I've mentioned a million times already, is C2V. Okay. But what if it had no reflection plane that was in line with the primary rotation axis either? So what if it had no reflection planes at all? Now, there's two possibilities. If it doesn't have a reflection plane in line that is right with the primary rotation axis, it's going to be an S2N group. Now if it doesn't even have an S, or if it doesn't even have an S operation, then it's just going to be CN. So we're going to talk about those a little later. You don't encounter them too often. The CN is encountered more than S2N, but I'll do some examples of those later. And but for the basics, again, you just want to see, is it low symmetry? Is it high symmetry? If it's no for both of those, then you need to figure out if it's C family or D family. And it's D family if it has two perpendicular C2 axes at least. And then if it only has one main rotation axis, it's C family. So, and then in D family, there's two choices. And for C family, there are four choices, but usually it's in the top two. If not, it's going to be CN. It's hardly ever S2N. So, we're just going to talk about these cases when we come back, and have a good one.